So let me introduce our next plenary talk. Automotive industry is experiencing a very exciting revolution. Cars are rapidly becoming a personalized mobile information hubs, and soon will be able to operate autonomously. Personally, I can't wait for my car driven on itself on the way to work every morning so I can catch up on emails. Connectivity is essential for the future car. Today, we're pleased to have Mr. Lars Reger of NXP Semiconductors presenting his vision on the road ahead for securely connected car. Ms. Lars Reger is Chief Technology Officer of Automotive Business at NXP, the world's largest automotive semiconductor supplier and the technology leader in the securely connected car. As CTO, Lars is responsible for managing new business activity, solution strategy, and R&D for NXP Automotive. NXP has a leading product portfolio in technology that enable the securely connected car and self-driving car of the future. A special focus of NXP R&D is currently set on solutions for security against hacking or advanced driver system. Prior to joining NXP in 2008, Lars worked for microelectronics companies including Siemens, Infineon, Siemens VDO, and Continental, always with a focus on automotive technology. Lars holds a university degree in physics from University of Bonn and an executive MBA from London Business School. Please join me to welcome Lars.
Yeah, good morning, everyone. I'm really pleased to be here, and of course, a great opportunity for me right after the wedding of Freescale Semiconductors and NXP in December. That makes us not only the biggest crypto chip supplier in the world, but also the biggest automotive electronics supplier in the world. And right up front, I have to apologize. In 1986 and 1987, I was a teenager in secondary school and was mainly focusing on impressing the girls in the neighborhood, but definitely not via papers or university contribution. And now that I'm standing here, I have a son at the same age. And what I can say is that he definitely will see in automotive electronics more innovation and more disruption in the next 5 years than I have seen in the last 30 since 1985. And what you have seen here, this little intro video, is a video that we do together with the company Rinspeed. And Rinspeed, Frank Rinderknecht, the owner of that company, is basically doing every year since 40 years, a concept car for the Geneva Auto Saloon. And one of those concept cars is this Tesla here, where you are autonomously driving, movable steering wheels. You're sitting opposite to the driving direction, if you like. So really innovative cars, crazy thoughts. And I, as a CTO of NXP, of course, I like that very much to playing with that electronics, with that ideas, and showing how much semiconductors, little tiny chips, can do in our everyday life. And well, as we have heard it this morning, of course, why is NXP so big in automotive electronics in the meantime? Well, NXP, the former Philips Semiconductors, was always a big supplier for car interfaces, so connecting everything to, from, and within the car. And that's, of course, for the analysts, especially at the stock exchanges at the moment, a great thing. It's a fantastic trend. Yeah, everything is going to get connected, and hooray, we're seeing an exponential demand. The other thing that I just said prior is, of course, there's a lot of microcontrollers, a lot of brains needed for all of that smart thingy, smart electronic that we are talking about. But there is even one thing that is more important. At the moment, in surveys, we see that 60 to 70% of all of you are skeptical on autonomous driving. You've heard about the technology, you think that machines eventually can do a lot, but you do not trust that your car really should drive you. And one of the big fears is, of course, data security, hacking security. You've seen that in the press over the last years. So Andy Greenberg, the journalist who hacked the Jeep last year, is, of course, there very prominent in the press. And here, another trend that fuels NXP comes nicely into the game. So as I said, we are the biggest crypto chip supplier. So if you have your wallet in the pocket, you're sitting on NXP chips for sure. This is in the Amex cards, banking cards, e-health cards, and 3/4 of all biometric passports. Remember that the biometric passports are important for that story of how connected devices get an identity. So basically, we are in the middle of that nice trend. Back to automotive. What are the key trends that are fueling automotive? And by the way, 95% of all innovations in automotive are semiconductor electronics related. Well, to the very left, that green pillar there is the old stuff that I also saw 30 years ago. Yeah, seamless connectivity. I want to be connected, like in my living room. I want to hear radio stations. Want to talk via hands-free kits. Want to have TV in my rear seat entertainment systems. That is unexciting stuff. The orange part is way more exciting. Everyone wants to have cars who consume carbon dioxide rather than produce cars with carbon dioxide, even Volkswagen nowadays. And this is, of course, a trend where especially also Californian cars are, or car makers are pretty pushy in the industry. I very much like that disruption that is coming in to that industry from that angle. For me, the most exciting trend is that center part there, this bluish part. Why? Well, because it describes a very strong disruption. It describes that in the last 100 years, we have thought of cars and vehicles of horse carriages that by accident have a combustion engine. Today, we start looking at robots that by accident have 4 wheels. And that is a bit of a different perspective, of course, to the whole industry. And new players, so robotics players, IT players, suddenly come in, and it's not only anymore about metal bending and welding. The cool stuff is that at the moment, we are seeing 1.3 million road fatalities every year. And with that automation, of course, one of the key goals that we techies try to achieve is drive this down to 0. So making sure that 1.3 million moms, dads, and kids every year come home alive instead of staying on the road. And is that realistic, or is that nerdy talk that I'm doing here now? Well, look at these tables. The fun story, or the truth, is that 94% of the road fatalities and heavy accidents are caused by human error. So it is not by a failure of a tire or of an engine or a real physical breakdown of the car. No, it is recognition errors, decision errors, performance errors. And there, of course, the hope is pretty high that a self-driving robot never is tired, never gets irate, never is talking to the kids on the backseat, never is doing SMSs, never is disturbed by a phone call, never is drunk, and never is tired. And with only that, traffic can get so much smoother that, point one, we can avoid loads of traffic jams on the roads. We can save massive fuel if we are carefully communicating with our environment, and that we basically make the life on the roads much easier. We cannot only widen the roads and put more concrete in our countries just to cater for the increasing traffic flows. Yeah, so clear goal from my side, get the human factor out of that equation. When I'm talking about car connectivity, you might have asked yourself, oh, what exactly is he talking about? There's lots of wireless interfaces already today to the car. Well, car radio, AM, FM, digital, satellite, and TV. Car access, so car keys, even the range over 1 kilometer of distance and open and close the vehicle. So long range crypto remote controls. We have wheel speed sensors, of course, for the ABS systems. We have connectivity, Bluetooth, Wi-Fi to the portable devices. We have a very massive in-car network. So the wiring harness is the second heaviest device in a car next to the engine block. And of course, we also have for the ADAS, advanced driver assistance systems, quite some sensors, camera, laser, and radar. And what I'm going to talk about today is this group of technologies that you see here. So it is vehicle to vehicle, vehicle to infrastructure technologies that are giving the car the ability to get information, real-time information outside of the line of sight. Yeah? With that, the car suddenly gets better than the human being. I, as a driver, can only operate in the line of sight. Or in other words, in Star Wars language, my car suddenly gets telepathic capabilities. It knows what's going on outside of the area that I can see. Security, hacking security I'm gonna touch, radar systems I'm gonna touch, and of course, then the changes that we will see by these self-driving robots in the in-vehicle networks. Well, and when we talk about such a robot is in theory always built up out of 3 components: sensing, thinking, and acting. Sensing its environment, trying to get as much context info in. There we are basically in a robot replacing the human senses, as I said. And here on that slide, this is car-to-car communication. This is the wheel speed sensors, radar, camera, laser, for example. And then, of course, you need a brain of the car, or like the auto guys call it, you need to do sensor fusion. You need to bring all these data streams together and make sure that we are 100% reliable there. Then, of course, when that sensor fusion is done via the neural network, so via the wiring harness of the car, we are sending the information, but this is tiny bits of information only. It's velocity vectors to each wheel, and this is direction, accelerate, or braking. And by the way, then a bit of additional information, of course, lighting adjustments, smart lighting, where I can drive in high beam and don't blind the people who are approaching me anymore, and all that sophisticated stuff. But by and large, that's the simple setup. And all of these ingredients, this is the great news, our new NXP has at the moment, and this is why we are talking basically to that whole automotive ecosystem so much from a silicon vendor perspective. What can we enable 2-3 years literally down the road? Well, you might have said, okay, yeah, we know these type of features, this type of sensing and robotics. We know already from the game consoles, consumer electronics, last boring stuff, go home again. Yeah? There is one thing, or 4 things, as you can see here on the slide, but this tetrahedron, that is one thing that we need to do different in automotive electronics than in normal consumer electronics. We have to make sure that these robots never fail, or as little as possible. Never is, of course, never possible. But what we need to do is the following. We need to make the devices as reliable as possible. If you have hundreds of thousands of electric components in a premium car, and each of those components has a certain likelihood to fail, you don't want to start calculating what happens and how often these cars break down just by single component failures. And this is what we have regularly in the press. Then, the automotive industry has mastered a process that we call functional safety over the last years. So this is risk assessments of the entire car. What could happen? How high is the fatality rate, fatality likelihood, if a certain subsystem component function fails, power steering, for example? And how do we build in redundancy? The road safety, we need, of course, to increase, as I said prior, getting the human equation, the human factor out of the equation. And there is a new thing that I've called here in that green bubble functional security. What we will see in future is not only these risk assessments, system risk assessments, how high is the fatality rate if a power steering collapses and then if the battery circuit switches off, but also how high is the likelihood for failure if a hacker attacks the car. And this is this famous GPEG example that I used prior. What you can see already on the device reliability, there is basically the automotive failure rates and the cumulative automotive tolerated failure rates way lower than the consumer industry. That is a static picture as of now. I know already that a lot of the mobile phone producers as of today cannot tolerate that anymore due to economic reasons, and also in medical industries and in other industries, of course, everyone tries to get as low to that blue curve there as possible, because that's, of course, burning a lot of money, callback actions. And the automotive industry has improved over the last 10 years big time and has to go even further. And why? Well, look at that slide. If you have in mind that per year about 90 million vehicles are delivered, and you're looking at these 3-year figures of callbacks, then the conclusion is a simple one. Last year was not only the all-time high year of car shipments, it was also the all-time high year of car callbacks. And this is definitely not tolerable, of course, for the car makers. And a few of the big cases have happened here in the US. Another one, as I mentioned prior, I'm going to expect this year from the German ecosystem. So going into a few of these examples, what are the key ingredients for changing the architecture towards these self-driving robots? Well, I've said it before, there is, of course, very much research going into these wiring harnesses, and I saw a picture this morning from Xerox on the Ethernet part. Of course, Ethernet is widespread in the industry, yeah? So we have it basically everywhere. And the automotive industry had proprietary bus systems so far. How old school is that? Yeah? So basically the idea, of course, now of the engineers was, hey, can't we steal from the computing, from the aircraft industry? Can't we bring in Ethernet into cars? Simple, yeah. Go to the consumer computer industry, buy it, bring it in. It was not that easy, because a regular 100 megabit line, as we have it at home, has 4 wires. And the last thing that you want to see is doubling the weight of that wiring harness here from 30 to 70. In a Mercedes S-Class, it is already in the 770 kilo domain, yeah? And just by doubling the wires. So the idea is, of course, next to these LIN, CAN, and FlexRay buses that we have in the vehicles and that are there in billion volumes, go into Ethernet, but go into 2-wire Ethernet, into robust Ethernet via an unshielded twisted pair cable. So far, story pretty simple. Yeah, okay, technically should be realistic. This is existing in the industry. Broadcom had that standard and we have licensed it. It is called Broad Reach. We have then implemented our own circuitry simply because we need to make this standard that was made for voice over IP systems, we need to make this automotive robust. Yeah? And the idea was, of course, clear. We want to have it reliable, cost-effective, all these big wishes. Today, 100 megabit going to gigabit in future. So all of that is clear. We have a broad software base. We have the microcontrollers, so that ecosystem is standing. And then we only need to do a few things. Make it temperature robust, minus 40 to 125 degrees centigrade. Make it EMC, so radiation and emission robust, and basically being able to have a lot of vehicle diagnostics inbuilt as well. And that is basically the value creation that we do with the standard chips in the automotive domain. You can go even further. We have the FlexRay system in cars, which is a synchronous bus system, which is used for all these X-by-wire applications. Yeah? So brake by wire, steer by wire, and accelerate by wire. It's very important to have a deterministic system, because the last thing that you want to have in a brake-by-wire case is that the system says, okay, Lars, I do now a one second wait state, come back in a second, and then I start braking. Does not work. But Ethernet, time-triggered Ethernet, deterministic Ethernet, would be an option even for those use cases. So what does that mean? Over one Ethernet wire, you have basically packages of data that you're pumping in, and these packages are these little cars that you see there. The car, the red one, is my ambulance that has the critical information. Now I want to do an emergency braking, so that package of data needs to go with highest priority. All the others are pulled back, and they only are slotted in with their priority later. So these type of abilities one has in an Ethernet network, and that's of course fantastic because we do not need to have a second redundant network in place, but we can use that immediately. Furthermore, what we will see is car networks are getting way more complicated. So Mercedes S-Class, just to stay with that example, has 150 to 160 control units. That's huge. Yeah? And in these old-fashioned car networks, you had one CAN bus, and then you had a few control units linked to each other. In the meantime, that IT system of a car looks like a big building with these 150 different rooms, and they are, of course, split in separate compartments, which is a good idea from a security point of view. So if someone intrudes one branch of that network, he cannot automatically screw up the other side of the network. So you don't have easy access if and only if this thing, what is called body domain there, is secure enough, which is basically the gateway. So basically the entrance hall of your house. You need to have a few watchdogs or Dobermen sitting there and waiting that no one goes from left to right. Of course, you have the Ethernet physical layers in there, and you have Ethernet switching architectures. So really the stuff that we know since years from an IT network perspective are all coming back now big time with a bit different flavor, but big time in the automotive industry. And what can us bring this? Well, very simple. What we have at the moment in premium cars is we have up to 20 euros of coax cables between the roof antenna and the navigation system in the center stack. 20 euros. Yeah? If I only can take out this amount of heavyweight coax cables and go to the car makers and say, hey, guys, come on, we make a deal. I get 10 euro more for my chips. You can use an unshielded twisted pair cable instead. So you reduce your system cost by 10 euro. I get the other half of that equation. Then they have a system cost saving. And basically what we are doing is we are aggregating all reception electronics in that shark fin antenna and only having a cheap digital pipe down to the automotive qualified digital tablet in the center stack. Furthermore, what we can do with this Ethernet PHY, with the physical layer silicon, we have used a serial link over that silicon to just glue satellite antennas in a very cheap way via an unshielded twisted pair cable to that main antenna, which is very, very important. Just imagine you have cars with a curved roof, and you have the shark fin antenna in the very, very end of that roof. Yeah, then you cannot see it from the front. So you have a very poor antenna reception. So what you can do is 2 unshielded twisted pair cables to the wing mirrors, and you have a 3 antenna system on that car. For convertibles, of course, perfect, and very, very simple to realize. These new type of architectures we see coming into the cars as we go ahead. Well, then one other thing, the advanced driver assistant systems, or as the automotive guys always say in the cryptic language, ADAS. If you want to have sensors that allow your car to be self-driving, you need to have basically a surround view around the car. And normally we have these park distance controls as of today. They have a maximum range ultrasonic 5 meters, in good cases 6-7 meters, which is of course nothing if you're on a German motorway at a speed of 250 kilometers an hour. These 8 meters are a joke. So what you need is, you need basically to have a radar cocoon that is at least 250 meters far looking to the front and at least 100 meters around the rest of the car. And for that, there's one technology very, very well suited, and that is basically radar. So if you only could have enough radar sensors around your car, then basically you have an adaptive cruise control to the front, you have blind spot detection, lane departure warnings, and also you can very, very accurately measure the range if you want to park your car. So far, these 80 gigahertz systems were pretty bulky and clumsy. You needed silicon germanium for the front end, then the basebands, microcontrollers, and the like. And 2013, some of my guys came to us and said, hey, Lars, we can do also 80 gigahertz in CMOS. I said, no freaking way that you're going to realize that. I don't believe you. They convinced me. Christmas Eve 2013, we taped out. And we have, in the meantime, a little tiny module. And there at these radar antennas, you see it in the bottom part, that little black block. This is a CMOS 80 gigahertz send receive unit, a radar unit. And why is CMOS so important? Well, because next to that NXP device, there is a Freescale radar microcontroller in CMOS. And now the game of the semiconductor industry starts again. Hey, if you have 2 times a CMOS chip, can't we make 1 out of it, and can't we drive the system cost down? So in other words, yes, this is what we are doing, and the Google engineers here in Mountain View are working with me since 1.5 years on exactly that type of silicon. We have very, very good measurements. Basically, that thing is usable for park distance cases, but also for the far range activities. And we are even clustering systems, 4 of those Dolphin chips, as we call it, into systems where we have 12 send, 16 receive antennas. And then, of course, you get maximum high brightness radars. So this is basically the core ingredients for self-driving cars. And, well, of course, for us, another disruption in the way how we run our self-driving robots. I was talking about telepathy some slides prior. Car-to-car communication is nothing else than the normal IEEE 802.11, so Wi-Fi, but there is a derivative that has a few bells and whistles in its standard, so the 802.11p. And this is basically a real-time, few milliseconds signal transmission with priority channels and a bit more to allow real-time communication in traffic. It's not a Wi-Fi as you know it from home that is basically ranging from your living room to the front door. No, these systems we have tested at a range of about 1 mile in open field. So in Ingolstadt at the Audi test area, we have tested it over 2.3 kilometers line of sight. And these systems work up to relative speeds of more than 500 kilometers an hour. What is the use case by 500 kilometers an hour? Well, very simple. One fast car on a German motorway and another fast car on a German motorway, they approach each other, they need to talk to each other, and each of these cars can easily drive 260 kilometers an hour. So basically, they have to exchange the messages. That's the use case. And Anthony Fox, US Minister of Transport, is very much pushing for getting a legislation out still this year for the few use cases that you have seen here, emergency braking, so in case you cannot see that a car in front of you is braking, overtake warnings, hazardous locations, an emergency vehicle, and crossroads, intersection assistance. But what you also can do is, of course, with these type of electronics, you can do car-to-traffic light communication. So basically, if I'm a bus in a smart city, I can tell the traffic light 500 meters ahead, hey, I'm bus 11 and I'm in 500, 490, 480 meters with you. Please make sure that I am at the maximum likelihood in the middle of the green phase with you so that I have a smooth flow. I don't need a lot of braking and accelerating, so fuel consumption goes down and public transport gets accelerated. The same thing, of course, for ambulances. Yeah? I am an ambulance, make sure I have a free road and I can drive. What if there were no security in those systems? Well, I can tell you what I would do. The first thing is a little test beacon in front of my house. Here is a heavy accident. Because then all of you take a big detour around the area where I live, and I can invite my friends for a nice barbecue. I have a quiet area there. The other thing is my car gets a little test beacon and says, I am an ambulance because I want to be 10 minutes earlier in the office, and I have the green wave then myself, until you find out you do not trust the system anymore, and you say, what's a cheating thing here? I do not invest in that type of technology. So in other words, car-to-car communication will only come if I have crypto security. Well, unfortunately, I could steal in my sister division and say, hey guys, you have passport chips. Can I get some? Can I get them automotive qualified temperature-wise? Because here nothing else happens than if I go to the United Airlines gate and hold up my biometric passport and say, hey, I'm Lars, I'm allowed to fly here at that gate. this car holds up its computer chip, so to say, with its hidden identity and says, hey, I'm an ambulance. And my passenger car can only hold up on a passport and say, hey, I'm a passenger car. So the traffic light, of course, would say, okay, if the street is empty, I'll give you priority, but that's basically what you get and not the ambulance use case. So what are the standards using? There is, at the moment, the standard in the make for this digital signing of the messages that you send. Because what you want to have is, of course, you want to communicate all these messages, hey, here is an emergency, or I have to do an emergency braking. You want to communicate in plain text, but then, basically, like in every electronic document, you undersign this digitally via a certified signature. It's a PKI type of system, public and private key. Most of you know that way better than I do. Elliptic curve algorithms are used just because they are very, very efficient, computing power-wise, to verify these messages. And the challenge here is different than a banking card, and this is why we need to look a bit deeper into the silicon. The challenge is, of course, if you want to have one financial transaction, you are typically the slowest link in that whole chain entering your PIN number. Yeah? And in the end, of course, hidden, the ATM machine has tons of time to communicate with the bank. This is different in a car-to-car communication system because up to 1,000 messages in 1 second can flow in. You have to filter what are the relevant ones, and the relevant ones you have to verify whether they are really containing critical content and are real. Yeah? So quite a bit of difference performance-wise. The mechanism itself is the same. Okay, now that I'm at security, I'm going to spend a few minutes on that security topic. Well, and I very much like this law of Roald Beckstrom, who has basically said, well, in future everything is going to be connected. This is what you saw on my first slide already. Everything that is connected can be hacked. In other words, everything will be hacked in future. And for us, this is a great new market. So I'm standing here with one side of my face smiling, the other side crying. Of course, I'm afraid of hackers. Like 500 years ago, people were afraid of others moving into their houses or walking into their houses simply because they didn't have doors or door locks. And what we now do as semiconductor industry is we start selling, let's say, surveillance systems, door locks, and the like. Nothing else than that. And these crypto chips are one part of that. And just to explain a bit, what is that thing when I always say crypto chip? It's a standard microcontroller, nothing more than that. Just a plain vanilla microcontroller that is in a non-volatile memory storing key data. The only art of that entire game is to designing that microcontrollers in such a mess and such a spaghetti that none of you can find out which transistor is doing what job. And if someone of you would like to open up such a device and would like to look into it and like to find out via all these physical intrusion capabilities, so really X-raying, alpha particles, indirect measurements, and the like hotspots, so everything that we have in semiconductor failure analysis. If we would try to do that, then this thing reacts like in a James Bond movie. Detects that it's going to be hacked and blows up. So, of course, not blowing up in a big bang and then smoke. So the second part of the James Bond movie never happens. But basically the chip says, hey, Lars, I don't feel well. I'm switching off now, and please don't rely on me anymore. And this is also what you can expect from autonomous cars in future. Yeah? These cars basically might feel that they are getting attacked, pull over to the right lane, switch on the warning lights, and say, okay, Lars, now either you switch to manual driving and go to the garage, or you stop at all and don't move anymore. This is very likely what we're going to see in some of the cases in future. In other words, yes, we will have IT systems in the car. We will have a few door locks and doors and architecture constraints that we will need to take into account. And we have basically 3 Lego blocks that we, as NXP, are trying to introduce into the wiring harness and IT system in the car. This one is these secure elements, these crypto microcontrollers for the wireless interfaces. The second is, of course, all microcontrollers that we sell are getting, it's basically standard in the meantime, high security modules. So this is a bit inferior grade to a secure element, but still crypto cells on these microcontrollers. And then what we are introducing is in the CAN transceivers and in the networking transceivers, simple logic. Ask yourself, you're sitting in the car and the car network detects messages of saying, hey guys, the trailer hook has just asked for lowering all the windows or opening the doors. Then every one of us would say, hey, come on, trailer hook, how come that your control unit asked that or issues that request? That does not work. Yeah, stop that immediately. And these type of sanity checks, of course, a simple network can immediately do. I've talked now a lot about silicon and semiconductor chips. There is additional services coming up and are related to that. And the services that are coming basically is we have these crypto chips in our semiconductor sites. We manufacture them, and then, of course, what we do not want to, and this is high security environments, yeah, biometric scanners, iris scanners, and the like. And what we, of course, then do not want to do is to force the Continentals and BMWs of this world to work in similar environments just to protect the crypto information on those chips. So basically, each of those chips at the end of the assembly gets closed, like your banking card, completely locked, and is basically, if it would be hackable, only that device would be hackable and only that key could be retrieved of that one very simple system. Then these chips are soldered into the control units, are going over to the OEM, to the dealer, to the end customer, and only if the end customer switches on the telematics unit, for example, there is a link back to a database. This is the trust provider, the trusted service manager, and there the chip ID and the key ID and the personal ID of the end customer have to match, and then this chip is going to be switched on for operation. Basically, you have this every time you get from your bank, you get a new banking card, the ATM machine does this in the background when you enter the new PIN. But of course, the easy thing for us is that we simply can steal what they have. So in other words, for self-driving cars, consumers need to trust their cars. We, as industry, have to prove that the quality, safety, and security that we can provide to such systems is better than in an unelectrified manual-driven car. Some of the core technologies I've introduced, this is, of course, radar and advanced sensing solutions. This is car-to-car communication, car-to-infrastructure communication, Ethernet, and crypto electronics. And the fantastic thing is there is no need to reinvent a lot of standards, which easily in automotive electronics costs you 10 to 12 years, but we can steal from our sister divisions. And with that, one last thing, if you like to go out there to our demos, we have a demo out there in the other hall. This here is another thing that I have stolen from my sister divisions. It's a long-range RFID, so an RFID that works over 20 meters. And I'm the first one worldwide, so not in a Texan, but in a German license plate, who has this in. And I use this as a contactless badge. So I'm driving in and out of the NXP area in Hamburg, or my car drives in and out and says gate up, gate down. I've glued that little sticker here into the school bag of my 10-year-old daughter, and we then have fixed such a reader at a traffic light in Hamburg. So just imagine the use case of school bus stops at a traffic light, 40 little devils come out of that school bus towards the traffic light, and the traffic light can see, oh my God, 40 school kids. I better go on priority for the kids in green. And via the car-to-car communication, I warn Lars, mate, behave, slow down. Here is vulnerable road users at the traffic light. This is what we at the moment in Hamburg are playing with, and look at it as my personal contribution to getting rid of these 1.3 million road fatalities. What I definitely need is a lot of your smart brains here in the room to helping me further reducing that, and yeah, looking forward to a good exchange. Thank you.